Hello, Guillermo here. Today I want to talk about harmonics. I'll explain to you what they are, and I'll also show you how you can reproduce them yourself. So let's dive right in. If you fix a rope by both of its ends, you can have it vibrate at all of its different modes. As you can see here from the graphic, all of these modes are multiples of the base length of the rope. Now, length and frequency are inversely proportional. So harmonics are exactly the same. Harmonics are exact multiples of the base frequency. Now, only the exact multiples of the base frequency will manifest as harmonics. The rest are just potential waves that never manifest. These potential waves are seen here with the dotted lines. So if you start at a given base frequency here in blue and start increasing this frequency, you would only get a harmonic once this frequency is exactly double as much as the base frequency. In this case, we have reached the second harmonic, which is the first octave. If you keep increasing the frequency like this, you eventually get at the third harmonic, which is the fifth. Increasing even further, you get to the second octave, which is our fourth harmonic, and so on and so forth. So what ends up happening is that the higher you go up in the octaves, the more harmonics you can fit within one octave. So you go from 2 to 4 to 8 to 16 to 32, 64 harmonics per octave, and so on. I made another video where you can hear exactly what the sound of these first 62 harmonics are if you follow this link. Oh, hi there. This is my monochord, and it's a very similar setup to that used by Pythagoras over 2,500 years ago. Basically, it's a set of stretched strings, but we only need one. According to our theory, if we split the string exactly at the ratios that we just saw, we should get exactly those harmonics. So let's have a look. So this is my bass tone. And according to theory, if I touch the string right at the middle, I should get the second harmonic, which is the first octave. There it is. Remember that we're measuring length, so the ratios are inverse. And what happens if I move slightly left or right? Nothing. There's nothing there, only where it should be. Right there. The third harmonic is the first fifth and should be, according to our ratios, right at 40.5 centimeters. Right there. Right on spot. The fourth harmonic is another octave. Should be right here. The fifth harmonic is the major third. Should be right around 24.5 centimeters. And the next one is another fifth. The next one is the minor seventh, which should be right here. And then we have another octave. Beyond that, we just keep getting higher harmonics. In this case, the major second. There it is. Then another major third. And then my favorite, which is the tritone. And then another fifth. So like we said before, the higher you go in the octaves, the more harmonics fit inside the same octave. What this also means is that for higher harmonics, the distance between two harmonics is always decreasing. The perceived pitch between adjacent harmonics is always approaching zero. And this is very interesting because that means in the very, very high range of harmonics, you almost make no difference between one note and the next. Check out my monochord video where you can hear all the range of harmonics, from the bass tone all the way up there to the highest pitches that humans can hear.